You should be able to share.
Yeah.
Okay, let me try.
Who is the John Pippin Chair in Microelectronic Systems, Packaging, and Electromagnetics at the School of Engineering and School of Electrical and Computer Engineering, and is also professor in electrical and computer engineering with a joint appointment in the School of Material Science and Engineering. He's also director of the 3D Systems Packaging Research Center, the PRC, down in GeorgiaTech. He also serves as site director for the NSF Center for Advanced Electronics through Machine Learning. Prior to his work at GeorgiaTech, he worked at IEEE on supercomputer systems. Madhavan, please.
Great. Are you able to see my screen?
Yes.
Okay, very good. Thanks, Phil, for that kind introduction. As Phil was mentioning, my name is Madhavan Swaminathan and I come from GeorgiaTech. And today the topic is on 3D integration, call it trends, challenges, and opportunities. This is some of the work that's ongoing here at GeorgiaTech. So I'll take you through the vision that we have and the work that is going on. So I serve as the director of the Packaging Research Center here and affiliated with the School of Electrical and Computer Engineering and Material Science and Engineering as well. So as an outline, I'm going to start with what I call as the market and the technology drivers, and then very briefly talk about the state of the art in 2D and 3D packaging. So it's going to be a very holistic view. I'm not going to get into the specifics. Very briefly discuss the challenges. And most of my presentation, I'm going to focus on glass packaging. This is work that's been going on at GeorgiaTech for some time, mainly on the 3D side and less on the 2D side. And then try to conclude with my take on the future of semiconductor systems. So let me start with the market driver. I believe, I'm sure all of us agree that we are entering or entered the big data centric era. And if you think about this data centric era, computing at the edge is going to become very, very important. And it's going to be all about integration and data movement. So when you're trying to move data over very long distances, the cheapest way to do that is through wireless communication. And then you need to be able to process that information and then feed it back so that you can do some very intelligent or embed intelligence as part of your communication as well. And when I look at computer processing and you're looking at movement of data, you're basically moving data over much shorter distances. And that is where this whole concept of intelligent digital RF convergence comes in. That is shown over here, where you have a front end that is all wireless, broadband wireless, and then you have the back end that is doing a lot of the computer processing for you, including the inclusion of your neural networks for intelligent processing. Now, when you're trying to build a system like this, I think all of us agree that you need to bring together a lot of technologies together, such as wireless, compute, photonics, sensing, control technologies, and many others on a single platform that I call as a package. And as was mentioned in the previous talk, energy efficiency is very, very critical. So when you move data around, you want to do it at very low energy per bit, and that becomes a very key requirement. So that is really coming from the market side. Then there is a technology driver that I'm sure all of us are familiar with by now, the need for heterogeneity. Now, if you look at the ICs that we are trying to build in very advanced nodes, we are all realizing that yield is becoming a big problem. And therefore, for you to get higher yield, you need to work with smaller dies coming from advanced nodes and find a way to connect them to each other using very high density interconnects. The second is this shorter time to market. So you want to work with smaller dies from optimized nodes that allows you to enhance functionality. This is an example from AMD that's doing exactly that, where you have a 7 nanometer process die, 14 nanometer process dies. They're all interconnected together through this package or interposer. And the third is, if you look at semiconductor systems that are emerging, they're highly heterogeneous. So it's practically impossible for you to just work on in the compute area, or let's say in the wireless area. You need to bring different kinds of IC technologies together that includes both the 2D integration as well as the 3D integration. And you want to do that as part of, let's say, an interposer that contains a lot of embedded functionalities, such as the antennas and things like that. So that comes more from the technology side. So given all of this, let's take a look at what some of the requirements are. And I'm going to spend more time on the compute side and just share with you a few slides on the wireless side, given the amount of time that I have. So if you look at high performance intelligent computing, there are 4 different kinds of metrics we need to look at. The first one is, of course, the energy per bit. So you want to keep this energy per bit as small as possible. The second is, if you're trying to connect dies along in a 2D kind of a direction, then the system bandwidth with units of gigabits per second per millimeter becomes very important. And this is what was mentioned by Tanay in the previous talk. The third is this IO pitch. Now, this IO pitch is directly related to the system bandwidth, but when you begin to stack these chips on top of each other, that IO pitch becomes very critical, because the amount of density that you get grows as the square of the area. So that becomes very important. And the fourth is this thermal design power. As you go from one node to the other, there is generally around a 6% increase in thermal design power based on the work done by AMD. And you need to find a way to support that. And some of these thermal design power requirements are getting close to around 1,000 watts or so. So if you look at where the technology is, clearly we want to go in the direction of this arrow. And you start with some of the available technologies. I've just shown a few of them. They take you only so far, including the silicon interposer. And I'm just going to call that as prior art. And the question is, how do you go beyond that such that you are able to get to very low energy per bit, high system bandwidth, very dense or a small IO pitch, along with much larger thermal design power. So, so let's look at what the advanced packaging landscape is. I just call it heterogeneous integration, but at the end of the day, you're trying to connect these chips together using some kind of a substrate technology. You can break them up into 2 parts. One is 2D and the second is 3D. And if you look at 2D, so clearly there are various different types of materials you can make use of, different kinds of constructions. So for example, we heard about the EMIB technology from Intel, the silicon interposer technologies, say from TSMC, lots of organic interposer technologies available. We are working on glass, others such as LTCC and silicon micromachining. If you go to the 3D side, you can broadly classify them into what I call as TSV based and non-TSV based. And with TSV, you can either stack chips using these micro bumps and TSVs, or you can make use of hybrid bonding. And depending on which path you take, there is a certain penalty that, or a certain advantage that you get. Now, if you look at the non-TSV based kind of a solution, it's a very different way of being able to connect chips vertically as well as horizontally. And that is really what I'm going to talk about today. We call this as 3D glass embedding. So when you work with these kinds of advanced substrate technologies, there are 3 major issues that one needs to worry about. And I'm going to go through each one of them very quickly, trying to make a case for glass. The first is the core material that you make use of. So if you look at this core material here, you're making use of glass. And there are some 5 properties that become very critical when you're trying to make or choose that core material. And there is a reason why silicon is being used quite a bit. simply because it has a very small surface roughness. It has a CTE that matches that of silicon. The Young's modulus is fairly high, so it's a stiff kind of a material, inorganic material, so there is no moisture absorption. It has a very high thermal conductivity. And if you look at a lot of the organic-based solutions, there's only so far you can take it in terms of the metrics that I showed you. But one of the options we have as a replacement to silicon is this glass-based technology. And if you look at the first 4 kinds of properties that one is looking for, it's quite good compared to or similar to silicon, except that its thermal conductivity is very low. So if you look at the advantages of glass over silicon, one of the nice things is the tailorable CTE. So you can tailor the CTE of this glass substrate such that it matches or it is close to that of silicon on the top and close to that of the PCB at the bottom. So it allows you to maximize the first and second level reliability. The other thing is what is shown at the bottom here. You can go to much larger package sizes simply because you're working with much larger panel sizes. This becomes very important when you look at a lot of the AI types of applications where the substrate size is going to grow much larger than the 35 millimeter size that is typically supported for silicon interposer types of solutions. The disadvantage of glass over silicon is, of course, the lower thermal conductivity, but you can use this to your advantage in certain scenarios and also find a way to work around this, especially when you're trying to use flip chip types of solutions where you can remove the heat from the top side of these chips. The second is the ability to pattern fine lines and spaces. Now, if you go from the left to the right, the key takeaway here is the lines and spaces, where if you look at some of the advanced organic-based technologies, you're looking at a number of roughly around 25 microns, and you want to get to as close to 1 micron or less as possible so that you have enough density in that substrate to be able to connect the chips to each other. And that is what is shown here as 2D. And of course, this 3D part also is very important that allows you to create the vertical connection between the chips. And what we've been able to demonstrate so far using glass is to be able to get down to around 1.5 microns in terms of line width and spaces. The third is the chip assembly at fine pitch. All of us are familiar with solder-based interconnects. And one of the nice things about solder-based interconnects is that it allows or gives you the compliance when you're trying to assemble a chip onto a substrate that is not that planar. But clearly, if you want to scale the pitch, you need to go to other kinds of approaches similar to this copper-to-copper bonding. And what I show as a technology gap arises when you're trying to take a planar surface such as a silicon chip and you're trying to assemble it onto a substrate that may or may not be that planar. Question is, how do you account for that? You need some level of compliance. And we believe that with a lot of the glass-based solutions, there is a possibility to be able to get to very fine pitch with these kinds of solutions. So with that, let me get into the meat of the presentation, which is on both 2D and 3D integration combined. And I think this is very, very important moving forward. 3D alone is not sufficient. This is an example of a glass substrate that we fabricated recently. Once again, this is a mechanical substrate at this point in time. What it shows is that you have 2 SoCs here that are connected to each other through the glass substrate. You also have the high bandwidth memory on the top that is assembled onto the glass substrate. But inside of the substrate, you have a cavity that is containing this die. This embedded die could either be a bridge die similar to the EBIP solution that Intel uses, or it could be an active die. It really depends on how you architect the system. Now, if you look at the thickness of the glass itself, it's 260 microns. And we are able to accommodate different thicknesses of these dies that we are able to embed into the glass substrate. So think of a solution where you can use this bridge chip as a way to connect the HBM to the SoC, or this embedded die could be a memory die right beneath the SoC that gives you this vertical connectivity. So how do we go about building this? So let me quickly go through the process. So we start with a cavity glass, a laminated cavity glass to bare glass substrate. So this is the glass, and you see this pink material that's an adhesive, and you have a carrier at the bottom. So we create this cavity, then we embed the die, then we do this dielectric molding using a dielectric material. Then we drill these microvias to make contact with these pads. We use a SAP process to be able to define the RDLs. And then we assemble these chips on the top using thermocompression bonding along with capillary underfill. So the process flow that I showed you, here are some pictures in terms of what we've been able to achieve. So we start with a glass that is anywhere 150 millimeters or 300 millimeters in size. This is a square glass with cavities in it. Then we place the dies in it. And this is what you see after die embedding. Then we do the dielectric lamination. We build our metallization levels, and you have a complete package. Now, clearly this 3D connectivity is very good, very important. But along with that, the 2D connectivity is equally important when you're trying to do this kind of integration. All of us are familiar with the EMIB solution that Intel came up with, where you make use of this bridge die in the substrate as a way to connect these dies to each other. More recently, AMD announced this elevated fan-out bridge for 2.5D, where if you look at this bridge die, it directly connects these two dies together without having to embed this in the substrate, thereby reducing the parasitics. We do something similar, except that if you look at this connectivity 2D, it's a direct connection using these vias between these two chips. So this is the 2D interconnectivity that I just mentioned. And in addition to that, you have this vertical connection as well. So you see this HBM can be placed directly on top of this SoC that is indicated here. Now, by embedding dies, we can reduce the assembly loss parasitics quite a bit. So I'm referring to these microvias that make contact to the pad. I'm trying to compare that with a flip chip and let's say a flip chip and a wire bond solution. And if you look at this table and this graph here, these are actual measurements where we are able to get down to around 0.15 dB of loss at 140 gigahertz with these kinds of microvias making direct contact with the pads, which is half the loss compared to flip chip and much, much lower than the loss that you get with wire bonds. So we are able to reduce the parasitics quite a bit. Now, what can you do with it? And this is work that is ongoing. It's not complete. Let me just try to share with you what we're trying to do on the signal integrity side. So we took this dual core RISC-V benchmark in the 28 nanometer process. The monolithic die is shown over here. And if you look at it, so you have a logic tile, two logic tiles, and then you have the memory here. We said, what would it take for us to break this up into 4 chips, connect them together in the substrate? And that is what is shown over here using the glass interposer. So you have 2 chips on the top. There are 2 other chips, the memory chips that are embedded in the cavity right beneath these 2 chips. And of course, with the silicon interposer, you have these 4 chips that are connected to each other. Now, if you look at this table, it's very interesting because what we were able to show is that by using this glass interposer solution, you can actually reduce the overall area of the solution even compared to this monolithic solution that is shown over here. It's much, much smaller. Of course, there is a certain penalty, around 12% increase in power, because when you try to go off chip using these AIB drivers, there is a certain power penalty that you have to pay. But what is interesting over here is the reduction in the footprint by going with this glass interposer technology. And if you look at the table, you don't need very fine wires in glass. It's basically 2 microns lines and spaces as compared to 0.4 microns lines and spaces for silicon. In spite of that, we are able to reduce the footprint simply because we are able to make use of these 3D connections or 3D connectivity. So let's look at what happens from a signal integrity standpoint. So if you look at this vertical connectivity here, the die that is assembled on the top has an IO pitch of 35 microns that's making direct connection to the pads with the embedded die. And you can you can see the thicknesses of the dielectric layers over here, as well as the dimensions of the vias. So if you assume, let's say that you want to go after a bit error rate of 10 to the power of minus 12 with a certain value for the I height and the I width, we believe that we are able to get to close to around 17 gigabits per second per IO, leading to a bandwidth density of more than 9 terabits per second per millimeter squared. Now, if you take this now and put it in the context of the other two 3D solutions that I showed you, which is the 3D stacking with micro bumps and the hybrid bonding, and just follow the last 3 rows over here, you will notice that the energy per bit can be roughly 3 orders of magnitude lower as compared to a 2D or a 2.5D solution. And it compares very favorably with this hybrid bonding, okay, and much lower as compared to when you make use of this micro bump, and you get a large bandwidth density along with that as well. So with that, given the amount of time remaining, let me very briefly talk about integrating the wireless side. Now, the question that we need to ask ourselves is, assuming you have this technology that is, let's say, suitable for the digital compute side, can you make use of the same technology and the same or a similar approach for the wireless side as well? And that is what is indicated here. So think of an access point, right, that is sending out these beams to a bunch of handsets over here. And you want to come up with a glass-based solution that addresses the access point here, the wireless access point, as well as the handsets. And if you look at this example or this cartoon that is shown over here that corresponds to this access point here, you can think of an antenna array at the top, a lot of the phase shifters that are embedded into the layers here, and with the glass core, with cavities containing all of the dies, similar to what I showed you earlier, except that you have the wireless dies embedded as well. And with this kind of an embodiment, you want to try and remove the heat from the bottom side. Now, to be able to get the right bandwidth, right, you need to get to sub-terahertz frequencies going beyond 5G to 6G, where scalability of the antenna array becomes very critical. And as you go to higher frequencies, the lattice spacing that you have, or the spacing between the antenna elements, is going to reduce quite a bit. So there's hardly any space for any wiring between these antenna elements. And as a result of that, you have to embed the dies beneath this antenna array. And that is the concept that is shown over here. So the goal is to be able to get to a loss of less than 1 dB, going all the way from the power amplifier that is embedded in the glass core, all the way to the antenna array at the top. Without getting into much details, let me just flash some of the recent results. So what we do is use a similar process that I showed you, except that the die thicknesses can be different here. And these are through cavities. So the back side of the die gets exposed once we remove the carrier. And this is some work that we have done using the Corvo die. So this is before the lamination. Then we laminate the die using a 30 micron ABF material. We do the laser drilling. So these are the holes, and the diameter of those vias are around 30 microns or 35 microns. And this is the panel showing the embedded dies, including the vias. So we've been able to integrate lots of antenna structures as well as other passives. There's just one example I'm going to show you. This is what goes into a handset. So there's a 1x4 array, and this is a Quasi Yagi antenna array, where the beam is transmitted this way. So this represents the director, and then the ground plane represents the reflector, and then you're providing the necessary feed lines here. This behaves like a monopole, so there is no balun over here, which was what you would typically use or include if you're making use of a regular Yagi array. So if you look at the actual fabricated structure, it looks actually pretty good. And if you look at the measurements, we are able to get a gain of around 8 dBi and very broad bandwidth covers the entire D band from 110 to 170 gigahertz. So the thermal management, as I mentioned, in this particular example, you're exposing the bottom side of the die, you're pulling the heat from the bottom side, and that requires the use of a thermal interface material. So if you just make use of silver epoxy along with a heat spreader over here, you should be able to remove the heat up to around 150 watts per centimeter squared. If you go beyond that, you need more fancy solutions like making use of these vapor chambers and cold plates. But one of the key things over here is that thermal interface material. The property of that material becomes very, very critical in terms of the amount of heat remove. And if you look at the simulation here, that corresponds to the temperature you would see on this PA die when you're removing heat from the bottom side using air-based cooling. So with that, let me try to conclude just by showing a couple of slides. So this is a comparison between this panel level fan out that I described so far using glass embedded packaging. And it's being compared with this eCIFO process, the SCAE mode of Infineon, as well as the TSMC Info process. And what I show here are the various embodiments of this glass-based solution. This is for wireless. This one is for wireless as well with a BGA connection. And these two are more for compute types of applications, depending on how much heat you can actually support. But the key thing is, if you look at how it compares with what is out there from a fan-out panel level packaging standpoint, we actually are compare quite well. So with that, let me show this last slide. This is the future for semiconductor systems. I think we all agree that when we think about future systems, it's going to require heterogeneity covering multiple length scales, and that is what is indicated here. One part comes directly from the transistor side, and this is what I call as the brain. But then you have this wafer-to-wafer bonding, 2.5D, 3D packaging that's going to play a very, very critical role. And that, to me, represents the body, right? The brain and the body have to go together. This is what you need for system scaling. So therefore, moving forward, the focus needs to be on bringing together the various functionality that I mentioned earlier on a single packaging platform, where this platform is going to play a very, very important role in terms of enabling high energy efficiency. So with that, let me conclude here. Thank you so much for attending this talk. And if you have any questions, I'll be very happy to answer.
Okay, thank you. Are there any questions from the audience?
Yeah. So cost wasn't us, and I guess the cost question is that TSMC and Intel have made the decision in a fork that we showed about going to TSV or non-TSV, and they're all working on HDI. So how does this fit in? They've already made that decision. I'm assuming that cost is a driver. So if it's energy efficiency, but it also has to be based on cost. So my question is, how does this compare that with cost standpoint? It just seems like that decision.
The question from the audience here is, have you looked at your
Phil, your voice is breaking quite a bit.
Can you hear me now?
Yeah, much better now. Yeah.
Okay, maybe I was too close. The question on this end is, have you looked at your solution in terms of cost comparison to the other options that you're comparing to, and drawn any conclusions?
I heard part of that question, Bill, but let me try to understand. I think it's cost related. Am I correct?
Cost of your solution versus the other solutions you're comparing to.
I understand. So the way we look at cost is, obviously a lot depends on the kind of volume we are trying to go after and things of that nature. as well as the throughput. So the way we look at it is, we work with much larger panels. So the size of these glass panels can go as large as 700 millimeters on a side. And as you go to larger size substrates, where you need to build, let's say, substrates of the order of 50 millimeters or larger, we believe that when you're trying to work with such large panel sizes, it's going to be quite cost effective compared to other solutions. Having said that, please realize that what I'm showing you, or what I showed you, is one embodiment of where you can make use of glass. But you can have different ways by which you can connect these chips together. So for example, you can make use of this bridge chip, where that bridge chip could actually be glass as well, that you can embed somewhere else. So what I'm showing you from an integration standpoint, we believe is going to be quite cost effective simply because of the panel size that we're making use of here.
Okay, thank you.
Yeah.
Questions? Yes, we have one here.
Yes, so what's the relative maturity of this? And then, who would I go to if I want to use this today?
Okay, the question is, what is the relative maturity of your technology, and who would the contact person be if someone wants to get more information on that today?
Phil, once again, I can barely hear you. Is the question what is the status on glass, or?
So, oh, that doesn't work.
Yeah.
It's the volume is okay on this end, so I'm not sure the problem is. The question is, what is the status of your technology? Who is the contact person at Georgia Tech? Someone should make contact with to get more information.
Sure. So the question is, what is the status of the technology, and who should they contact at Georgia Tech?
Yes.
So you have my email address, I think, visible. Please go to our website, prc.gartech.edu. There's a wealth of information there. Or also send me an email. Now, in addition to that, the status, I'm not sure if all of you heard this. Around 2 weeks back, there was a big announcement by SKC to build glass-based substrates in the state of Georgia. So it's a huge investment being made by SKC based on technology developed at Georgia Tech's Packaging Research Center, where they're going to get into production in 2023. So things are moving forward as far as glass-based technology goes.
Did he say 2022?
He's talking about SKC, like SK Hynix.
Yeah, I so you said, was you implying that this will be production ready in 2024?
No, what they're putting into Georgia.
My question is, when will this be ready?
We have a question on this end of when you think your technology could potentially be production ready.
Lost you again, Phil. I can't hear you. Yeah, it's constantly breaking, so I don't know why.
Do you have any idea how long your technology would take to make production ready?
Oh, how long is it going to take for our technology to be production ready? Am I correct? Okay, very good. When you talk about manufacturing, we are a university, we do pre-competitive research, and getting it all the way into manufacturing requires an intermediate step, which is basically development and prototyping. And that is something we do not do, but we try to work with the companies as a way of doing technology transfer. And that is how SKC basically took the technology from here, getting that into manufacturing, because they work with us very closely with engineers on campus, developing this technology. So we have similar kinds of arrangements. So one of the companies we are working with very closely is Qorvo on the RF side. As you know, Qorvo won an RF center recently called SHIP, the state-of-the-art heterogeneous integration program. We are part of that, working with them very closely. One tiny part is on glass-based packaging that we are working on. So the hope is that as a lot of these applications emerge, for each one of these applications, there is a different type of a construction that you need based on glass that would work. And that, so therefore, what we are trying to do with Corvo is quite different compared to what we did with SKC. But things are moving forward.
Okay, thank you. That is the answer we're looking for in this.
Mhm.
Any other questions? Okay, if not, we'll take a break for 25 minutes and start up again and with our Vanguard panel session in 25 minutes. Okay? Thank you, everyone.
Great. Thank you.